Okay, we're on chapter 3 here. Continuing on in chapter 3, we were talking about bonding. We're talking about really the two types of bonding. We have ionic bonding, which is always between a metal and a non-metal. And always in this case, we do get a transfer of electrons from the metal to the non-metal. The result of that is, as we talked about, we will make a cation from the metal, which is positively charged. We will make a anion there from the non-metal, which is negatively charged. And once again, these two are held together by the attractive force of the positive and negative attraction. There's absolutely, again, no sharing of electrons that are occurring here. It's that electrostatic attraction between these two guys. And that is different than a covalent bond. And a covalent bond, it is typically between two nonmetals. And in this case, it is sharing of electrons that are occurring. And as we talked about last time, the sharing of electrons may be equal sharing, may be unequal sharing, but there's some aspect of sharing that is happening in a covalent bond. So on one end, we have the ionic bond as we finished up on, where we do have the transfer of electrons. On the other end of the stream, we have a non-polar bond or a non-polar covalent bond, which is the equal sharing of electrons. And sort of in the middle is a polar covalent bond, where we have unequal sharing of electrons. So on one end, we get a complete transfer of electrons, really because of a lot of those periodic trends we talked about, where the nonmetals pretty much want the electrons, want to bring electrons towards themselves. The metals don't really want to hang on to their electrons or anything like that. So that works really well for the transfer of electron to occur, resulting in a fully positive and fully negative charge occurring in our ions. As opposed to polar and non-polar, which are both covalent bonds. They're both really between two nonmetals, which share very, very similar periodic trends like electronegativity, electron affinity, ionization energy. And again, what basically happens with those two guys is they will decide to share electrons rather than transfer. And really based on electronegativity as to whether or not those electrons will be shared equally or unequally. The result of that is in a polar bond, we do end up with a side of the bond that is more negative, which is sometimes represented by drawing this dipole arrow, where it points to the more negative side. And the back end is to the more positive side of that bond. The more negative side would be obviously where the electrons ended up. The more positive side would be the least electronegative atom within that bond that occurs. Our partially negative charge and a partially positive charge develops on a polar bond. Again, they are partially positive, partially negative because they are still sharing the electrons, so they haven't fully transferred, but they definitely are not being shared equally to each other. In an ionic bond, we saw we could use Lewis symbols to help us understand what's going on. And when we do something like that, we use one dot for each valence electron. We have a transfer of electrons from, say, the sodium to the chlorine. The result of that is our sodium will then gain a positive charge. Our chlorine here will pick up the electron and become negatively charged. And once again, when you do draw sort of Lewis structure for ionic compounds, they really should have the bond in there. The purpose of ionic bonding and really covalent bonding, as we'll talk about and have talked about a little bit, is basically everybody wants to get to the same electron configuration as the noble gases. So something like sodium, which loses its one valence electron, backs up on the periodic table to helium's electron configuration, which makes it really stable. And chlorine, which picks up that one electron, moves forward to argon's configuration and that makes it very happy and very stable. Now, sometimes, as we talked about, you may need more than one metal or non-metal to sort of get everybody to that sort of completed octet, if you will. Like we saw with the, I think, calcium and the fluorine. When you put those together, you do need actually two fluorines to handle both of the electrons for calcium. By having both fluorines, that allows each one to individually accept one electron and get each of them to neon's configuration, and the calcium then is able to lose two total electrons, one to each of the fluorines, and back up to argon's configuration, which makes it really happy as well. Any questions on any of that stuff we talked about last time? Yeah, so the proper ionic bond, when you write a formula for an ionic compound, should always be neutral. So all the positive ions and negative ions, their overall charge should balance each other out. And really, the real reason for that is what we saw with that calcium and fluorine. It allows everybody to reach basically that kind of noble gas configuration when you do that in the simplest way that gets to zero, basically. Yeah. Other questions? So once again, the ionic compound for sodium chloride would have a formula that looks like this. It does not have a charge written in the formula, but it is made up of two things that do have charges. Obviously, the sodium with +1 and the chlorine with a -1. Other questions? Okay, so let's continue on here. So really, what helps us decide how the electrons will be shared or maybe not be shared is really electronegativity. And once again, electronegativity is that ability of an atom to bring electrons towards itself, increases as you go up and to the right on the periodic table, with fluorine being the most electronegative element, and decreases left and down on the periodic table, as we talked about. It is related to electron affinity and ionization energy. So something like fluorine has a very high electron affinity and a very high ionization energy, and they both basically mean it's going to pretty much gain electrons and hang on to its electrons. And sodium, on the other hand, has a low electron affinity, which means it's probably not gaining too many electrons, and has a low ionization energy, which means it will not be too hard for it to lose its electrons along the way. Now, how can we determine, if we put two things together, whether or not we will sort of get a equal sharing or unequal sharing of electrons? A guy by the name of Pauling came up with sort of a scale that we use for electronegativity. 4 is the most electronegative value, 0 being obviously not so much. Yeah. So he gave values to pretty much all the elements from 0 to 4. And we could use really the differences in the electronegativity values to help us determine whether or not we will yield a polar bond, a non-polar bond, or even an ionic bond. Although you really don't need electronegativity values to help you with that. So if you take the difference in electronegativity, which is what that is, the change in electronegativity, and you basically do it by just subtracting the two values. If you get anywhere between, say, 0 to 0.4, that is considered usually a non-polar covalent bond. Anywhere from above 0.4, which would be like 0.5 usually, to below 2 is some type of polar bond or polar covalent bond. And not in all cases, but in most cases, above 2 will result in an ionic bond. So basically, in terms of sharing, what we're talking about here, non-polar means equal sharing. Polar means obviously unequal sharing. And ionic means no sharing, right? A transfer. of electrons basically happening. Another terminology that is sometimes used, especially for a nonpolar bond, is one that is sometimes classified as a pure, which is really a nonpolar bond. It is when you have an electronegativity difference of pretty much 0. So you get electronegativity difference of 0. It is basically considered perfect equal sharing of electrons. It's a nonpolar bond, and it's sometimes referred to as a pure covalent bond because of that perfect equal sharing of electrons. Yeah. You would be no, you would be fine. I personally would still call it a nonpolar bond, but some books and some people will call it sometimes a pure covalent bond. So if you hear that, basically what they're talking about is a nonpolar bond, and they're specifically talking about like perfect equal sharing of the electrons in that case, yeah. But it's still, because it's equal sharing electrons, it's still classified as a nonpolar bond. Other questions on that? Okay. So this is a table of electronegativity values. So if we look at some of the ones that we did previously, I think we had some sodium chloride. We had some HF, and we had some F2, I think. So if we were to use these values here, we would simply just go and find each of these elements. So if we did sodium there, it is 0.9. And if we did chlorine, it is 3. So the change in electronegativity would be 3 minus 0.9. That is a 2.1. 2.1 is above 2, obviously. So that means that this should be an ionic bond, which it is. Do I really need those numbers for this? The answer is no, you don't need the numbers for this because it is a metal and a non-metal, which means it's going to be ionic. So you don't even really need the numbers to tell you that. As soon as you see metal and non-metal, you should know it's an ionic bond. There's no sharing of electrons. So for ionic bonds, you don't really necessarily need the electronegativity values. And there are cases where you will take a metal and a non-metal and actually will be less than 2 and it's still an ionic bond. So it's not a perfect number for ionic bonds, and you don't really necessarily need it. If we look at HF here, H is 2.1, fluorine is 4. So once again here, if we took the change in electronegativity, it would be 4 minus 2.1, and that is a 1.9, I believe. 1.9 is obviously below 2, above 0.4, so it is a polar bond. And this is pretty much not equal sharing of electrons. It's almost to the point where we would consider the electrons transferring out, but we haven't got there. So it's still barely hanging on. And that again is why we would draw our dipole arrow pointing towards the fluorine, which is more electronegative, and the hydrogen is more positive because of that. If we look at F2, we got a 4 minus 4, which obviously if we take the difference there, that is going to be 0. So this would be a nonpolar bond, and this would also be an example, as we were just talking about, a perfect equal sharing of electrons, which would also sometimes be classified as a pure covalent bond because of that. Any questions on that? Yeah, so in this case, we just want the difference. So you take the larger number, so you get a positive number. It's all good. Yep. Other questions? As we also talked about, right, electronegativity values end right there at fluorine, because to the right of fluorine is the noble gases, which are not looking to do anything, right, because they're perfectly stable the way they are. So if you ever need an electronegativity value for it, most people just use it as 0 in terms of electronegativity for a noble gas, because they're really not looking to gain electrons, lose electrons. They're perfectly kind of fine the way they are. So why don't you try some here, decide using the electronegativity values. Are these bonds ionic, polar, or non-polar? Let's do CH. Let us do let's do KS. Let's do CO. Let's do PN. And let's do perhaps DS. All right, so for each of these, calculate the change in electronegativity and determine whether or not they are ionic, polar. Okay, let's take a look. So again, we'll start with the carbon hydrogen here. So carbon is 2.5, hydrogen is 2.1, which means when we do the difference in electronegativity, we got 2.5 minus 2.1, going to give us a 0.4, which means this is going to be what type of bond? It is going to be a non-polar bond. Now, again, the difference between sort of a pure covalent bond and a non-polar bond, even though they're both non-polar bonds, is even though this is a non-polar bond, are the electrons being shared perfectly equal? They're not, right? They're kind of hedging just a hair towards the carbon, but not to enough of an extent that we would consider it sort of unequal bonding or unequal sharing of electrons. Plus, they would have to rewrite all the organic books because pretty much all of organic chemistry is carbon, hydrogen, which is the basis of the non-polar bond that we see there. Let's take a look at K and S here. So K is 0.8, S is 2.5. Difference in electronegativity of 2.5 minus 0.8. That's like a 1.7, I think, in this case, yes. This is going to be, it would be polar based on the number, but what are these two things? That's a metal and a non-metal, which means, again, that 2 cutoff is not perfect in every situation. And this would be an example that it is actually ionic here because it is a metal and a non-metal. So again, that sort of 2 cutoff, it works in a lot of cases, but there are some combinations of metals and non-metals that come together that will be a little bit less than that. So that's why I say you don't really need electronegativity for ionic. As soon as you recognize metal and non-metal, just roll with an ionic bond and you should be good. Any questions on that one there? Carbon, oxygen here. Carbon is 2.5. Oxygen is 3.5. Difference in electronegativity here, 3.5 minus 2.5. Again, just taking the larger number gives us a difference of 1, which means this is going to be a polar bond. Yeah, because of that. Going to draw the arrow, it would go towards the oxygen in this case, right? It is more electronegative. Are phosphorus and nitrogen. Phosphorus is 2.1, nitrogen is 3. Difference in electronegativity here is going to be 3 minus 2.1, 0.9, I think. That's going to be polar as well. Once again, it actually will shoot towards the nitrogen in this case. And lastly, our carbon, sulfur. Carbon is 2.5, sulfur is 2.5, which means the difference in electronegativity here is a big zilch, which means this is what type of bond? Is a nonpolar bond. And this is also a prime example of you absolutely can have 2 different elements that actually will share electrons equally. You for sure will have guys sharing electrons equally if they are the same element, but you could also obviously have 2 elements that are different. It is what is sometimes referred to as the diagonal rule here on the periodic table. We look at carbon and sulfur, they are diagonal to each other, 1 over. Carbon is further up, but sulfur is further to the right, so they sort of cancel out their differences in that case. Happens in a few places. If you look at nitrogen and chlorine, same deal. So you see it as you go through a number of different sort of locations here where you have this sort of diagonal relationship. So you do want to watch out for those occasionally because, you can't get those guys that are different that do share electrons equally. Yes, sir. You would be given, I don't know if you're given this exact table, but you would be given the values for the electronegativity values. Yeah. Other questions on that? Now, do you always need the table to make your decisions, or could you make a educated decision without the actual values? And the answer is you hopefully can make an educated decision. For example, if we were doing the carbon and oxygen one, carbon and oxygen's right there. They are in the same row or period on the periodic table. And we know oxygen is further to the right, which means it's going to be polar without the need of the numbers because it is further to the right. They are in the same period. Same thing with phosphorus and nitrogen. They are in the same group. And we do see that after I scribbled it out there, we see that nitrogen is further up there in that group, which means it should be more electronegative. So we could make sure we know it is a polar bond. So there's a lot of situations where you have things you're comparing are in the same group or the same period. You could use just the general trend in electronegativity, and you could make a pretty educated guess that they most likely will be a polar bond in that situation. And again, if you see something maybe in the non-metal region, that is sort of that diagonal relationship, not exactly right diagonal, but kind of over one in terms of diagonal, you might be into something that has the same electronegativity value, so you might want to check it. Any questions on electronegativity, how to use it to determine polar, non-polar, or ionic bonds? So obviously, as we saw, atoms with widely different electronegativities will definitely tend to form ionic bonds. And that's really always your metal, non-metal. Basically, metals on the left-hand side of the periodic table, non-metals on the right-hand side. And obviously, our covalent bonds are coming really from non-metal interaction, which are pretty much on the same spot on the periodic table. So a couple of things just to close out on this topic here. Again, as we saw, the 2 rule is a sort of a general cutoff. It works for a lot of ionic compounds. But once again, just looking at the metal, non-metal is really all you need on that. And sometimes people refer to, instead of sort of polar ionic, percent ionic character. So if something has 100% ionic character, then it is obviously an ionic bond and there's no sharing of electrons. Something has 0% ionic character, it's really a perfect equal sharing situation of non-metal and non-metal and the electrons that are occurring. Sometimes people refer to that sort of percent ionic character. All right, so we talked about drawing Lewis structures for ionic compounds. Let's talk about the proper steps that you should follow to draw Lewis structures for covalent structures. If you follow these sort of steps here, it should really lead you to a pretty good structure in most cases. If you choose not to follow these steps, then you'll get maybe something right or wrong. If you choose to do it in parts, like a lot of people try to do, or try to double bond, triple bond, and all that kind of stuff right out of the gate, you probably will end up with an incorrect picture, not enough electrons in the wrong spot, and stuff like that. So the first thing you really want to sort of figure out, or one of the first things that you want to figure out when you go to draw Lewis structures, is you want to figure out how is everybody sort of put together? What is sort of the arrangement of how the atoms come together? There are a couple of things that you could think about will help you to sort of decide. For the most part, the least electronegative atom should occupy the center spot. So that means usually no fluorine in the center because it is the most electronegative. Hydrogen should never ever be in the center because, as we talked about, hydrogen should only have 2 electrons. So if you slap it in the center, you are definitely going to have way more than 2 electrons happening there, and you don't want that to occur. Logic also helps in a lot of cases. If you've got, like, one element, an atom of one element and multiples of another element. A lot of times the one atom of that element's in the center, everything else is directly attached to it. There's not a lot of weird, funky arrangements as to how things normally will come together. If it is something that you may not be familiar with, I probably would give you a hint as sort of the connectivity of how it would go. But most things I would say that we come across usually in this class is there's like somebody in the middle and everybody's sort of attached to the guy in the middle is sort of how it works. Probably the most important thing is really the next thing, and that is you need to count up the total number of valence electrons there are. That means that if something does have a charge, you need to adjust your count of valence electrons. So if something has a negative charge, as we know, that means something has gained electrons. So you need to add those electrons into your total. And if something has a positive charge, that means that something has lost electrons. So you need to subtract that from your total. That number that you get here is the most important, because when you are done with your picture, you have to have exactly that number of electrons. You can't have any more or any less. You should also think of these electrons as not belonging to any particular element. And that is sometimes where people screw up. They go, well, carbon had 4 to start with, so it only needs maybe another 4, and they should come from here and there. And that is not a good approach. So you want to think of the electrons as sort of the total amount of electrons that you sort of need to distribute to everybody in that particular compound you're drawing, and not really belonging to anybody necessarily in particular. A reminder, the number of valence electrons equals the group number, right? So that's a very quick way that you could calculate how many valence electrons you got going on. Group 1 obviously has 1, 2, 3, obviously to 8. The next thing that you want to do is arrange your elements in the proper sort of arrangement. And you want to draw one single bond from the center to each of the outside atoms. And most people use lines to draw the bonding electrons. So personally, I use lines, but you could use dots if you like. But one line to each of the outside ones. Each of those lines represent 2 electrons. So you want to count up how many electrons you just used, making that single bond to everybody that's on the outside. All the remaining electrons should go on the outside atoms in pairs of electrons as dots, until each of the outside atoms has 8 electrons around them, or if it's hydrogen, no dots, right? And it will already have its one line that should take care of it. Once you fill up all the atoms on the outside with dots, and you still have electrons left, if that is the case, then you go to the center atom and you place the electrons on the center atom also in pairs. So pairs on the outside, leftover electrons, pairs on the inside guy. At that point, you should be out of electrons. If you still have electrons, you did something wrong after you put them all in the center. You should be out of electrons at that point. Last thing you want to do is make sure that everybody has met the octet rule. And it is that point where you have distributed all your electrons. And if you find somebody has not met the octet rule, that is really sort of the right situation to try to fix it. And we try to fix it by making a double bond or a triple bond to fix it. So you would want to try to exhaust all your double bonds at that point. If that still doesn't fix it, then you want to go and try to do a triple bond. At that point, a triple bond should definitely fix it. And then you would be good. So that's what I was mentioning. If you sort of follow these steps, it should really lead you to a pretty good structure when it's all said and done. Would always be the best structure, maybe not, but it will lead you to a pretty good structure when it's all said and done. You definitely don't want a double bond or triple bond right out of the box. Any questions on that there? All right, so let's take a look at one here together. Follow these steps. We have NF3. So the first thing we're going to do is calculate the valence electrons here. So nitrogen is group 5, which means it has 5 valence electrons. Fluorine is group 7, and there's 3 of them. So they each have 7 valence electrons. That's going to give me 26 valence electrons here. Again, my picture needs to have exactly 26 valence electrons. In this case, I have nitrogen and 3 fluorines. And since I have one nitrogen, I'm going to put it in the middle because fluorine is obviously the most electronegative atom you could have, so it should never find itself in the middle. So logical arrangement would be a nitrogen, fluorine, fluorine, fluorine. And at this point, we're going to do one single bond from the nitrogen to the fluorine. And we did 3 bonds, which means we have now placed 6 electrons. So if we subtract off our 6 there, we got 20 more to go. These are going to go on the outside ones in pairs. So we will go 2, 4, 6. That one is full. 8, 10, 12, 14, 16, and 18 at that point. At this point, we have basically filled up all the outside atoms. That means we still have 2 more to go. So that's going to be the center atom there. And we're going to lay up a couple of electrons right there in the center. At this point, we have now placed all 26 of our electrons. We want to make sure everybody's good in terms of the octet rule. Obviously here we got 2 electrons, 4, 6, and 8. All the fluorines are identical to each other, so they're all the same. Nitrogen has 2, 4, 6, and 8 electrons. So everybody has met the octet rule and everybody is good in that case. Yeah. Yeah. So that would be the case where you then would want to try to fix it by making a double bond. And if the double bond doesn't fix it, you would then want to go and make a triple bond. Hopefully that would fix it at that point. Yeah. Yep. Any questions on this one here? All right, so why don't we take a look at CO3 2-, which is carbonate. So why don't you first try it and then we'll talk about it. So take a look. So in this case, we'll count up our valence electrons. So carbon is group 4, I think. There are 3 oxygens and each one's group 6. I have a -2 there or -2. What should I do with that? We do add, right? Because the minus means it gained electrons and it gained 2 electrons. That's a lot of math there. 24 we'll go with. You do not. So the overall thing is the polyatomic ion. So the overall CO3 all stays together and overall has a -2 charge. Yeah. So in this case, in the center should definitely go carbon. If we look at carbon and oxygen on the periodic table, carbon is further to the left, which means it's less electronegative. And common sense says I only got 1 carbon, so probably we'll put it in the middle a lot of times here. So we're going to do carbon in the middle. We're going to do oxygen around. We're going to do our 1 single bond to each of the oxygens there. That uses up 6 electrons. That leaves me more after that to use. As that 18 maybe on that math? I don't know. Or we got something like that. We're going to put those on the outside. So 2, 4, 6. So that is filled. 8, 10, 12, 14, 16, and 18 at this point. I have now put all 24 electrons on my picture. Is my picture good here? It is not. All the oxygens have met the octet rule. They all have 8 around them if you count it. It is the carbon that is short. So I want to fix that. Can I fix it by doing this move? I cannot, because now how many electrons do I have? I have 26, which is too much. So this is the case where we do want to fix it by making a double bond. Doesn't matter which oxygen I choose. It doesn't. They're all equivalent. So we're going to make a double bond in this case. So can I just decide to do this? I cannot for the same reason. I now have 26 electrons. My oxygen's got way too many electrons happening in that case. So when we do make a double bond or really even a triple bond, what we're actually doing is we're going to take a pair of electrons and basically move them in to make that double bond. And when we do so, we will end up in this case with a double bond up on top. And you usually put a little bracket around it to make it look all pretty since it has a charge. And that will now be the proper carbonate Lewis structure. We still only have 24 electrons total. Carbon in the middle has 8 electrons now with the double bond. The double bonded oxygen on top has 8 electrons, and each of the single bonded oxygens also have 8 electrons. So this would be the proper Lewis structure for carbonate. And again, a situation where we would use the double bond to sort of fix that situation. As we mentioned, we could have double bonded to the left or to the right, which would also give you a little different looking Lewis structures if you did that. So if we did that, or if we double bonded, not there, we double bonded to the right. So we double bonded over there. All 3 of these structures would have been perfectly fine to draw, any one of them. They are all actually related to each other, sometimes by this arrow, type of arrow. These are what are known as resonance structures. And what a resonance structure really is basically the true structure here falls somewhere between all 3 of those Lewis structures, because those double bond electrons are delocalized, which means they're just flying around. So at any given point in time, they may be to the oxygen to the left, maybe the one to the right, maybe the one to the left. So basically those double bond electrons are just kind of moving around. So not one Lewis structure sort of adequately describes what's going on. So if you're asked to draw the resonance structures here, this is sort of what they would look like. In most cases, the resonance structure means that if you have more than one place to make the double bond, you could draw another Lewis structure where you just kind of move the double bond to the other location. If you're not asked to draw the resonance structure, you can lay up any one of these 3 structures and it would be perfectly fine, whichever one that you do. Any questions on that there? Okay, so let us draw a few more here, since we are Lewis structure professionals, right? All right, so let's draw nitric acid. Let's draw SO2. Let's draw CO2. Draw a little HCN, a little N2, ClO3 minus, NH4 plus, and finally NH2 minus. All right, so take some time here for each of these, draw the proper. Okay, let's take a look, see how we're doing on these. So we'll start with the first one, which is nitric acid. Nitric acid is what is referred to as an oxyacid, and all oxyacids pretty much have that connection right there, an OH group attached to it. That's actually what makes it the acid. That hydrogen is the one that comes off that makes it an acid. So that is sort of logical arrangement for these guys. We'll add up our total number of valence electrons. We got 1 for the hydrogen, we got 5 for the nitrogen, and we got 3 times 6 for the oxygen. That's 18, 19, 24 valence electrons here. In this case, as I gave you the logical arrangement, we're going to do a single bond to everybody in this particular case. That used up 2, 4, 6, 8 electrons. That's going to give me 16 more to go. We are again going to work on our outside in. Should I put any dots on the hydrogen? I should not. It is filled, so it is done. We'll go to the oxygen on the outside and go 2, 4, 6, 8. We'll go to the oxygen up on top, which will be on the outside. 2, 4, 6, and then obviously 8 completing it. The next sort of outside one would be the oxygen that's attached to the hydrogen. And at this point, we have attached 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. So we got 20 and then 24. I think I might have miscounted. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24 electrons at this point. So that's all 24 electrons. Is this structure good the way it is? It is not. What is wrong with it? It is the nitrogen. So once again here, we would need to fix it by making a double bond. In this case, really, there's kind of two options. It would be this oxygen, this oxygen. Once again, you probably wouldn't want to do that, although you could. But that is sort of the part that makes it an acid. So you probably want to double bond into that oxygen there. So we're going to take a pair of electrons from the top there. And again, I'm going to bring them in to make that double bond. And that would get me a structure that looks something like this. Which is nitric acid. We also could have done a resonance structure where we double bonded to this guy instead. And if I did that, I would obviously end up with a picture that looks something. I'm just going to put the oxygen on the bottom here, and that should be single bonded at this point. So drop the oxygen this way to save space. And those would be resonance structures of each other, except I am missing a hydrogen, so probably want to put the hydrogen on that guy as well. Not missing that. There we go. And hydrogen. There we go. So these would be two resonance structures of nitric acid. By the way, it doesn't matter. I drew the oxygen to the bottom or to the top. It doesn't really matter. Just like in the first one, it didn't matter if I put the fluorine on the bottom or I put the fluorine on top. It's all the same if you just rotate the molecule around. Any questions on that one there? All right, let's take a look then at SO2 next. So SO2 here, we got 6 for the sulfur, 2 times 6 for the oxygen. Looks like an 18 valence electrons. In the center here should go sulfur. It is in the same group as oxygen, which means it's lower down. It should be the least electronegative. We should have a sulfur in the middle, an oxygen to the right, and oxygen to the left. We're going to make a single bond to each of the oxygens, maybe. There we go. That is 2 and 4 electrons, gives me 14 more to go. That's going to be 2, 4, 6. 8, 10, 12. At this point, I still have electrons I need to put on there. And they do go to the sulfur in the middle, which is how they get the non-bonding electrons, not double bonded on every side like everybody likes to do here. And don't put the electrons there. That is how the electrons get there, and they should be there on that particular one. Any questions on that there? That is 18 valence electrons. That is all of them. Is this picture good? It is not. The sulfur is missing a pair of electrons. In this case, we could do a double bond to the left or to the right. I'll start with the left here. We're going to take those electrons and move them in. And this would be the proper Lewis structure for SO2. Not double bonded all around with no dots on the central atom. Once again, you could have done a resonance structure where you pretty much laid up the double bond on the other side. Any questions on that particular one? So again, you need to make sure you kind of follow the distribution of those electrons. It is a super common mistake that people make on this one. They never get the dots on the central atom. So again, if you follow sort of what we talked about, you should definitely get those dots on the central atom. Any questions on that one? All right. Then we got a little CO2 action happening next. Carbon is 4. There are 6 for each oxygen, and there's 2 of them. So once again, that is going to be 12 and 4 is 16 valence electrons. Carbon, once again, will be in the center as it is less electronegative. oxygen to the sides, single bond to each of the oxygens. That is 4 electrons. On the outside here, we'll put the rest. So that is 2, 4, 6, 8, 10, and 12 electrons, along with our 2 bonds in the middle, is our 16 electrons. In this case, is the carbon good in the middle? It is not. So we want to fix it here by trying to make a double bond. We will take the electrons in to do so. That will get us something that looks like this. Is it good at this point? It is not. Now, do I want to jump to a triple bond? I do not, because I still have an option for a double bond on the other side. So you kind of want to exhaust all your double bond options first. So we will take a pair of electrons and bring those guys in on the other side. And then that will get us our classic double bonded oxygens there on both sides, which would give us our proper Lewis structure. Any questions on that one there? All right, next up is HCN. So we'll go that one next. HCN, we got 1 for the hydrogen, 4 for the carbon, and 5 for the nitrogen. That's a whopping 10 valence electrons. In this case, hydrogen cannot be in the middle, and between carbon and nitrogen, carbon is the least electronegative, which means it should find itself in the middle in this case, and it should be an arrangement that looks something like this. We're going to do a single bond to each of them. That is 2 and 4 electrons. That gives us 6 more to go. We're going to fill the outside ones first. Hydrogen is done, right? Because it already has 2. So we'll put the rest of the electrons over here, 2, 4, and 6. That is 10 electrons. Nitrogen is good, hydrogen is good, but once again here, our carbon in the center is not good. It only has 2, 4 electrons. So we're going to try our double bond action. So we're going to bring a double bond in to do that. When we double bond it, we end up with something like this, which means we got carbon closer, but it's still a little short. It's got 6. At this point, we then would want to go to a triple bond in this case. Triple bond works the same way. We're going to take a pair of electrons and bring it in to do so. And when we do that, we will end up with something that looks like this, which now has 10 valence electrons, and everybody is good there. Our carbon has 8, or nitrogen has 8, yes. We put carbon in the middle because our choices were either hydrogen, carbon, or nitrogen. Hydrogen should never be in the middle. So when we look on the periodic table, carbon and nitrogen are sitting right next to each other. And that means in terms of electronegativity, since they are in the same row, the nitrogen should be more electronegative. So it's always the least electronegative that should be in the center. So that's why we chose carbon to put in the center. Other questions? That then brings us to nitrogen, which is N2. That's going to be 2 times 5, which is 10 valence electrons. In this case, there is no center atom. There's only 2. So arrangement here is pretty simple. We're just going to go side by side, perhaps. We're going to follow the same sort of process. So we're going to do a single bond in this case, which gives us 2 electrons, 8 to go. We're going to put them on the outside, 2, 4, 6, and 8. Here, the nitrogen on the left has only 4 electrons, so it is not good. So we're going to fix it by making a double bond and bringing that in. That gives me a nitrogen that's double bonded in this case. Nitrogen on the left now got better, but is still short. So we're going to triple bond, which was like your question the other day. This is why we triple bond nitrogen in this case, to get everybody to 8 valence electrons. At this point, we now have a triple bonded nitrogen, and each has a lone pair of electrons, which is what it should have. Everybody's got 8, and that would be our proper need here. So in the case of nitrogen, we had to go to a triple bond to get everybody to 8 valence electrons. Any questions on that one there? Terrific. All right. So we got then ClO3 minus here. So Cl is chlorine, which is 7 plus 3 times our 6 for the oxygen. -1 here means, again, we're going to add 1 to our total, just 1. And that would be 18, 19, and 7 is like 26, maybe. I don't know. Valence electrons. In this case, in the center should go chlorine, oxygen to the sides. We're going to do a single bond to each of them. That is 2, 4, 6, and 8 electrons. We've got a bunch more to go there, so we're going to put them on the outside. So 2, 4, 6, 8, 10, 12, 14, 16, 18. At this point, we have 24 electrons that have been put onto our picture. We still have 2 more to go, and those should end up right about there as pair. Put a little bracket around it and call it a day there. Yeah, so that would be the proper structure. Everybody's got 8 valence electrons, and we have used all 26 electrons. Any questions on that one there? Yes, sir.
Switch to the top O with chlorine.
Could you switch to top O with chlorine? You probably would want chlorine in the middle, if that's your question. Yeah. Why? So chlorine would probably be a little less electronegative than the oxygen and stuff. So and usually in a situation like this where you have one element by itself and 3 of the same, those 3 of the same usually are on the outside, and that one is in the middle. So to answer your question, we're going to talk about formal charge next, and that will help you decide whether or not it would be a good idea to do that or not. And based on formal charge, certain situations where you might want to run them all in a row would not be the best sort of picture. So you absolutely could move everybody around and sort of attach them. But there's something known as formal charge that we'll talk about, which helps you decide whether or not this picture versus this arrangement is maybe a better one and not a better one and stuff like that. But usually you probably wouldn't run all 3 of them together with the chlorine at the end or something like that. And I guess, yeah. Other questions? Okay. So let's take a look at NH4 plus here. So we got 5 for the nitrogen, 4 times 1 for the hydrogens. This is a positive, which means we are going to subtract 1 in this case, and that is going to give us 8 valence electrons. In this case, we got nitrogen and our hydrogens around. And there you go. That's going to be 8 valence electrons. So everybody's good at that point, and a positive, and we would be done. Any questions on that one there? Lastly, here we had NH2 minus. So we had 5 for the nitrogen, 2 times 1 for the hydrogen, and once again we will add 1 for that. That's going to give us 8 valence electrons here. Nitrogen would be in the middle. We would have hydrogens on the outside, and we would do 1 bond, 2 bonds, which is 4 electrons. We still have 4 more to go. They would end up on the center here as hydrogen cannot take any more. And that would be our structure going on there. Any questions on how to properly draw Lewis structures for covalent molecules in this case here? Yeah. So to sort of answer the question that was sort of asked, one of the things that we do use sort of in bonding to help us decide between, one sort of Lewis structure and another is something that's known as formal charge. And we could calculate the formal charge on all the elements that are drawn in a Lewis structure. And the formal charge is really the difference between sort of the total number of valence electrons in the free atom and sort of how it is attached and bonded in that Lewis structure that you put together. To calculate the formal charge, you take the number of valence electrons in the free atom minus the number of non-bonding electrons, those are dots basically, minus 1/2 the number of bonding electrons, which are lines. And here we're taking the total number of electrons, not pairs of electrons, but actually, there's 2, 4, 6, 8 dots, and using those as our numbers. So for example, one that we just drew, if we had our look something like this. So if we were to calculate the formal charge for each of the elements that are present, we could start with carbon. Carbon has 4 valence electrons in its sort of free atom. In our Lewis structure, the number of non-bonding electrons is 0, as there's no dots around carbon specifically. Minus 1/2 the number of bonding electrons. So if we count up the lines around carbon, each line is 2 electrons, 2, 4, 6, and 8 electrons. That gives me 4 minus 1/2 of 8, which is 4, which means in this arrangement, the carbon has basically a formal charge of 0. If we do our double bonded oxygen, in this case, the number of valence electrons in oxygen by itself is 6, minus the number of non-bonding electrons in the double bonded oxygen, which is 4, minus 1/2 the number of bonding electrons, which are the lines. Each one has 2. So that is 4. So that's going to be 6 minus 4, which is 2, minus 1/2 of 4, which is also 2, and that is 0. So in this arrangement here, the oxygen that is double bonded has a 0 formal charge. Let's take a look at the single bonded oxygen. And in this case, I can get it to draw. There we go. The single bonded oxygen has 6 valence electrons for oxygen. In this arrangement, it has a total of 2, 4, and 6 non-bonding electrons, minus 1/2 of a single bond there, which would be 2 electrons. That is 6 minus 6, which is 0, minus 1/2 of 2, which is 1. And the oxygen on the left there would actually have a formal charge of minus 1. The oxygen on the right will come out exactly the same, would have a formal charge of minus 1. In this arrangement, it is the single bonded oxygens that are actually taking on the more negative charge. Carbonate has an overall charge of minus 2, and that is where the minus 2 comes from the single bonded oxygen on the left in this drawing. The single bonded oxygen on the right is carrying basically an overall charge because of the way it's bonded in there, minus 1 and minus 1, which gives carbonate the overall minus 2 charge in this case. So you could calculate with, just like we did for any Lewis structure, that you draw the formal charge of every single element that's involved. And as we'll talk about next time, you could use the formal charges to decide, as your question was, if I wanted to, like, say, a nitric acid, instead of attaching the hydrogen to the oxygen, want to attach it right to the nitrogen. Would that be a better situation than how we drew it the first time? The idea, as we'll talk about, essentially with formal charge is this. The best sort of situation for formal charge is where you could really minimize it. So get everybody like to zeros would be the kind of the best thing. The next best thing, as we'll talk about, is essentially, if you can't get everybody to zeros, you typically want to have the more electronegative atom having the more negative formal charge versus the more electronegative atom having a more positive formal charge. And typically speaking, if you calculate formal charges on things and have really large ones like +2, +3, +4, those are most likely not going to be the best structure that would occur. So again, depending on how you arrange certain things, you can use formal charge to help you decide, which arrangement would probably be the best sort of Lewis structure. Any questions on that there? Yeah. Yeah, so really the best situation is like if you hit everybody at zeros, that's sort of the best situation. If you can't get everybody at zeros, but still have sort of low numbers for formal charges, the best thing you would want to look at is like if you have two elements and one's more electronegative than another. If you drew your Lewis structure and you calculate the formal charge, and your more electronegative element actually ended up with the more positive formal charge, that's usually not the good situation. You would want the more electronegative had the more negative formal charge or stuff like that. Yeah. Not necessarily. It's just you better have the negative formal charge on the more electronegative atom if you're kind of comparing, so say you have like a plus one minus one situation, and that plus one ended up on the more electronegative atom, that would not be the best structure. But if you had it the opposite way, where the minus one ended up on the more electronegative, then it would probably be a better structure. So like that. Yeah, so usually lowest numbers, not lowest numbers like negative numbers, but low numbers like ones and stuff like that. So if you start calculating formal charges for elements and they're like plus threes, plus fours, those are probably not the best structure. So they shouldn't be really that big. And this is really all based on sort of how you're distributing the electrons, right? And electronegativity is sort of happening. So in this case, because oxygen is really more electronegative than carbon in this situation, it's kind of pulling those electrons closer to itself and becoming more negative in this sort of situation than actually the double bonded oxygen in this case. Other questions? And we'll do some examples of sort of choosing between which Lewis structure would be better than another next time, probably. Yeah. All right. We will lay it up there for today.